Previously, we talked about breadth first search and depth first search. So now I'm going to show you something that will help you with this week's lab, part 2 of this week's lab. So just to refresh our mind, what's a depth first search? In the depth first search, you're going to go into one of its children, maybe like left. It's asked, do you have the value you are looking for? So let's say you are looking for the value C. It's right there. But in the depth first search, you're going to go to deep. You're going to ask these children, okay, do you have it? So this one said, you don't have it. So let me ask my children. Then it's going to go to its children and ask, do you have it? It say it doesn't have it. Let me ask its children. So it's going to go to the, let's say left or right. You can pick either. It's going to ask this one, okay, do you have it? Do you have it? No. So it's going to come back and ask its other children, do you have it? Then it goes back again. It asks, do you have it? So do you see it goes to the depth to see if it has the value you are looking for. I'm looking for the value C. So then it comes here and check, do you have it? Yes, you have it. So it's gonna return back the path. So here I will use a stack. In that stack I will have the path. In the breadth first search, what we did was we started here, then we looked at all its children. In the breadth first search, in two comparison, we would find the answer. But in the depth first search, you have to go deeper and deeper. So part 2 of the lab has to do with depth first search, this one. In this graph, let's say you start at 1 and you want to go to this second node. So what is the path from 1 to 2? If I were to use breadth first search, it would find, okay, from 1 to 2, there's a path, and it would find this path here, which has the distance 6. So with the depth first search, you would go from here to 0, 0 to 2. It will give me, okay, that's the path. So it's going to go into a deeper level and find the answer. So let's look at this piece of code. So this is basically the answer for that. So remember how we did the adjacency list. So I'm using adjacency list. So here I'm also inserting the distance part. So how do I insert the distance part? If you have a structure, you could add this part, the distance part. So now you have two values parts, distance and vertex. For the simplicity, I'm going to talk about this without the distance for now. So right, start equal 1. So I'm going to start here. I want to see what other vertices can I travel to. So if you start here, what other vertices can you travel to? You see there's a path to 0, 2, 3, 5, 4, all of them. But what if you start here? If you start was 4, do you have a path to any other node? You don't have a path. So here it should print out there's no path. If I start here, this should print out, okay, there's a path here, there's a path to this and that. When you do this lab, if you draw an array for the visited and the stack, you will see how this piece of code works and you can manipulate it to solve the part 2 of the lab for this week. Alright, so here, what is the start? I'm starting at 1. So here, what would be my start? This is 1. So here, every time I visited the place, I want to put a 1 in there. So right, so for that first location, I put 1 because I visited. So because I'm starting here. Then you're just going to print out that value because you are starting here, you're going to print out. So you would print 1 and Then I have a pointer node. So this is just to find its children's and travel through. So here, what am I doing? I'm using this adjacency matrix. In the adjacency matrix, I'm using this start. Start is 1. Because here start is 1, here start is 1. So if you say adjacency 1, which one of these is it correspond to? So this PTR, if you say this is corresponding to this location right here. So remember, this is whenever we did the create a graph, we had an array. We create a pointer array. So that's this one. So in here, everything is a pointer, something that can hold an address. So they will hold an address of a node. So here, this is a linked list. By the way, earlier whenever we called this function from the main with the value 1 for the start, that 1 got placed inside the stack. Then we went through these steps, so we are here. Now, since the start is 1, we are referring to this. So this is the part some people get confused. Right here, this is like a head node. Each one of these is like a head nodes. So these head nodes point into this right here. So that means this has become this node right here, the first node. So it's checking. Is this first node in here, in the while loop, it's checking. Is that node is null? Meaning, is it pointing to nothing? No, this right here has an address. So this become true. Then you also want to keep track of, have I visited that node? So for that, I have this piece of code. So at the beginning, this visited array right here had bunch of -5s to start with. So from the main, I made all of them are -5s. So if it is a -5, it denotes I haven't visited. So what is PTR's vertex part here? What is PTR's vertex? That's 3. Do you see? If you use PTR.vertex, no, let's forget about the distance for now. So I'm going to do this without the distance for now. Then I will introduce the distance. So let's say no distances here. All right, I removed all the distances. So all right, so here it came to this location. So what is in here? Which one does 1 is pointing to? 1 is pointing to 3. I mean the node 0, see? So, it's checking. So this value right here is 0. In visited 0, is it equal to 5? Is visited 0 is equal to 5? It is. -5, it is equal to -5. Because I haven't visited there. So since I haven't visited there, you're going to enter the body of the if statement. And what do you notice here? What kind of a call am I doing here? That's a recursive call. I am calling myself. So using recursion, I can solve it. You don't have to use recursion, but you can use recursion too. So this way I only have like few lines of code to write. So here I'm going to call itself with which value? PTR vertex is 0, see? I'm here. I'm going to call itself with the value 0. So that means I'm going to call this function with the value 0. Whenever I call it, I'm going to place it in the top of my stack. Because that's what will happen internally. Now my start is 0. All right, so what happened here? Let's go to visited start. So start is 0. So on that 0th location, I'm going to insert the value 1. Yeah, I inserted that value 1, then I print it out. So here I'm saying from 1 you can go to 0. So I'm printing out 0. So far I printed out 1 and a 0. So these are everything you can visit from 1. And again we do the same step. We update these PTRs. So what is start? Start is 0. So that means this PTR referring to this location now. Earlier it was referring to 1. So you see I'm moving through each node and its neighbors. Then it's checking. Is it null? Meaning 0 has become this one. This node 2. It's checking like, okay, do you have a node or is it null? You know, it's not null. I have something there. So you're going to go to this if part because this is true. Since this is true, you're going to go to the if part and you check this. So again, so now I'm not looking at the start part. I'm looking at PTR vertex. So what is PTR vertex here? Which is 2. It's checking. Is 2 is equal to -5 on the visited one. Alright, which means this right here. Is it equal to -5? Yes, it is equal to -5. So that means we haven't visited. So we're going to go through its children's now. One of its children, because of this recursive call, it's always call itself with one location. So that location in here is 2. So vertex is 2. So you're going to call yourself with the value 2. So the start now is 2. Alright, so just like before, I'm in here, start is 2, visitors 2 is this location. I'm going to insert the value 1 to denote I have visited there. Now I'm going to print out that value. That value is 2. So again, I'm saying from 1 I can go to 2 as well. There's a path to 2 from 1. And I have this PTR. Now I'm gonna update the PTR. So what is start is 2. So that means this PTR should point to this location. Now you're gonna check. Is it pointing to null? No, it is pointing to some value, 0. So you're gonna enter the body of the while loop and check. So what is this value? PTR's vertex value, which is this one, 0. So visited 0. Where's visited 0? Visited 0 is right here. Is it equal to -5? Is this equal to -5? It's not. It has the value 1. So this right here becomes false. So you are going to exit out. You're going to skip this if statement. You're going to skip it. You're going to go to this line. And you're going to make your PTR move to the next one. So earlier, PTR was pointing to this, the node with the value 0. Now, when you say update this PTR with this next part has the value of the next address, which is this one. So this PTR now will point to this node right here. Alright, so now it's pointing to the node with the value 5. So again, I'm trying to see all the nodes I can visit from 1, not a specific location where I want to stop. So alright, so We did this part next. So we are here. And so after this, where will it jump to? It will jump back to the top of the while loop. And it's gonna check for this. Is 5 is a null? Is this one is null? No, it has a value. Now this right here is gonna check. Is it equal to -5 in the visited array? So what is the PTR vertex value? Vertex value is this 5. Visited 5. Let's look at 5. Visited 5. Is it equal to -5? Yes, it is true. It's equal to -5. So you're gonna do a recursive call. You're gonna call yourself with the value 5. So this start becomes 5. Whenever that start becomes 5, whenever you call your function, you place its variable inside the stack 5. You know, these other things, adjacency and visited array, you know, I'm just passing those things. This middle part is the one that always change with different value, the start one. Alright, so I called it with 5. Then what do? I set that location, 5th location, which was here, equal to 1 because I visited there. Then you print out this value. You print out 5. Now for this recursive call, you're gonna update the PTR again. So adjacency 5th location, which is this right here. Alright, so that's the place. You check, you know, is it null? No, it's not null. It has a value. So you enter and you check. Is this value 2? PTR vertex is 2. You know, is it equal to null in the visited array? Okay, let's look at that location. Is it equal to -5? It's not. It has a value 1. So this right here becomes false. So you're going to go to the next part. You're going to update the PTR. Alright, so what happened? PTR was here. You're going to say this PTR should become its next part. Next part is null. So PTR will become null. So it's going to go back up and check is PTR is not equal to null? No. So it is equal to null. So this while loop become false. And from here, you're going to jump to the end. And there's nothing after that. And nothing after that. So you exit out. What happened when you exit out? You are done with that function call. So you're going to return back to whoever called it. So by the way, whenever you are done with this function, you're going to pop out that value from your stack. So 5 pops out. So who called 5? This one right here called 5. So the returns goes back to that location. So which was right here. From there we jumped here. So we are at here. From 2 we are going through all of its nodes. So alright, so let's say my ending node is 4. I don't want to go through all. I want to see if there's a path between 1 to 4. So that's what I'm trying to do. So we come here. So we are there. So who called from here to here? That was this recursive call. So I'm gonna delete the rest. Then I'm gonna continue back from this location. So what comes after this location? I mean, it returned back, right? So it's going to go to this next line and update the PTR. Now, PTR will point to this node. Then it's gonna, from here, it's gonna go back up and check, is that null? Is this PTR is null? It's not. So it's gonna come to this part, visited's fourth value, PTR vertex has 4. So is it -5? It is. So you're gonna enter the body of the if statement again. So here you could do a recursive call and keep going and keep filling up your stack and visited ones. So you understand, I can do this. I can go through this stack and visited, and it will tell me, it will mark 1, 1, 1 for each ones I can visit. But my point is I want to see, can I end at 4 if I start at 1? So just before this recursive call, you could have an if statement in there. If statement in there to see if you have found the ending value. If you found the ending value, you stop. You are no longer going to do any recursive call. All you're going to do is return back. Notice here, if you print out this answer 1025, that's not the answer. 1025. No. I want to know the path from 1 to 4. So that's why I said, if whenever you draw a picture like this, a diagram, it's going to help you. Look at this one. This 5 was popped out of the stack already. So I only had these values. So what if I just print out the values in here? That would be your path and that would be your answer. So where do you end? You end at 4, right? So after 4, if you pop out every single values, pop this out, print 2, then pop this out, print 0, pop this out, print 1. So this is a backward, but that's the correct path. Just like I showed you for the part 1 of the lab, you could assign this into array, then print it in backward order, but it's fine. I'm only interested in the path. So there would be an arrow going this direction. From 1, you go from 1 to 0, then 0 to 2, then 2 to 4. You see, that's the path. If you use depth first search, you get that path. And all right, so that's the answer. And how would you write a code for that? So in here, whenever you try to call yourself with the new value, you want to see, have I reached that value? Have I reached the end? If so, I want it to stop. So you could put this piece of code in that location. Meaning this right here should go in here. So what is it saying? If that vertex value, earlier vertex value was 4, if that value is equal to my ending value 4, I want to stop. At that place, I am going to record my total. I'm gonna have you can have like a global variable called total, and you can add the distance part of it to this total. Earlier total was 0, you have to initialize it to 0, then you accumulate values to it. then only at that location I am printing out my values. These 4 you can print out from the main, or somewhere. So the way I program it, this 4th one, last one wasn't inserted into the stack, so it will not be printed. But you can change this program in a way you insert that one into the stack as well. Or you can program it the way I did it. You just print out the ending one and the rest you print out in this manner, this order. It's fine. You can print out your answer in forward order or backward order. And then what you return 1. When you do return 1, what happened? You're going to return back to whoever called it. It's not going to execute any of the lines underneath it. This whole function is going to terminate and return back to its previous recursive call. And the other thing is, this right here, it's only going to get called 1 time. So this is like a base case. So this is a base case, so it's only get called once. On all other cases, I want to print out the values in my stack. Meaning, what values did I put into my stack? That was the start at every single step. All those start values, I put it into this stack. I want to print it out. Another thing you want to do is, you want to come up with another variable called found. And you're going to make this recursive call, which should return a value. So instead of this being a void, this should be int, because this is returning a 1. So that 1, I want to assign it to found. If found is equal to 1, that denotes that, okay, I found the value I am looking for. I no longer need to do any more calculations. That's why I'm returning a 1. So found will have the value 1. So if this is, alright, so, this one returns a 1. So this get us that value. Outside of this if statement, outside of this curly brace, if you write another function, if found equal 1, then I want to print out all the values in my stack. You will need this line of code too. You want to also add all the distance to it. So you would need this line in here as well. And you need to print out the value of this stack. So actually, if you just print out this start, print start, and from here also you should return a 1, because you don't want this function to go any longer. You always want to return back to its previous recursive call and assign the value 1. So that's right here is your answer. So I kind of showed you this briefly. So draw a picture whenever you program and look at it. Whenever you program something new, if you don't understand, draw it and you will find, oh, if I just print out this stack, that's my answer. So that's what I'm doing here. For the first time, I found the value at the, I print it out, then all other cases, found was equal to 1. If the found was equal to 1, what I did was print out this stack. So that gave me my path in the backward order. If you want, you can print it in forward order or backward order. Both is correct. So I emailed you, look at the output of the sample output I have given you. What I did was I put the arrow backward and print out your path like that. And at the end, just print out this total distance you found. So that's the answer.